And here we are continuing to work through chapter 18 on amides and amides. We've done pretty well, hopefully, on amines, and you're pretty comfortable by now, I would expect, with those structures and how they might occur and how we name them and why we care about them in this course. And so hopefully you're ready for the next part. And here we are ready to discuss amides. And we already mentioned that they're a pretty high priority group, a much higher priority than the amines. And we'll see why as we discuss the key structural features and nomenclature and all that good stuff that we have for amides. So looking at amides, they have an amino group that replaces the OH group, the hydroxyl group of a carboxylic acid. So that's why they're such a high priority, right? We said carboxylic acids are the highest priority group that we've discussed anyway in this course. And then we had the esters, and then third in line were the amides. And so you see they have a very similar structural feature. And we'll also discuss the idea of amide bonds when we're looking at proteins. So what's the preparation for these amides? So we can make them by heating a carboxylic acid with ammonia or an amine, a primary or secondary amine. Of course, we can't do it with a tertiary amine because we don't have the hydrogen to make that water that's our coproduct. And the process is known as amidation. So we're making an amide from a carboxylic acid and an ammonia or amine molecule. And so we see a couple examples there, both with propanoic acid or propionic acid by the common naming scheme. In the first case, we add ammonia, and so we get that amide bond, the carbonyl from the carboxylic acid and the nitrogen from the amine, or ammonia in this case, and then a water as our coproduct. In the lower case, now we see the same propanoic acid reacting now with methylamine, and we get N-methylpropanamide, so also having a water as a coproduct. Of course, biologically, we can't do it by heating, but we can do enzyme-assisted amide bond formation. So on the previous slide, you already saw a little bit of how we name these things. And in both IUPAC and common naming systems for amides, we have the carboxylic acid that would have been the parent, one of the parents, one of the reactants. We drop that IC acid or OIC acid ending and then add the suffix amide, no space. So we see there we have what would have arose from butanoic acid and ammonia. We call that butanamide, or in the common naming scheme, remember instead of butan it's butyr, so butyramide is how that would be pronounced. Okay, so if we look at the rules, or at least the steps here for applying those IUPAC names we discussed in the previous slide, first we're going to find the alkane name of the carbon chain from the carboxyl, so formerly the carboxylic acid, so up to and including the carbonyl, we replaced that E that would have been the name of the alkane chain for that number of carbons with amide. So here at this particular structure, the carboxylic acid would have been butanoic acid, so it's a 4-carbon parent that would have been butane, so we take the E and put amide. Next, we name the substituents on the nitrogen atom, if any. In this case, we do have a methyl group, so we use the prefix N- just like we did for amines, and in this case, we're going to see it's N-methylbutanamide. So there we have it, our IUPAC nomenclature for amides. And here's a couple other examples showing both the IUPAC and the common names. So we have our N-methylethanamide, that's the IUPAC name, or N-methylacetamide would be the common name. So just like we had acetic acid was the 2-carbon carboxylic acid, acetamide would be the 2-carbon formerly carboxylic acid that combines with the nitrogen to make an amine into an amide. For our other example here on the slide, we see again by IUPAC, it would have been a propanoic acid or propane. 3-carbon would have been the IUPAC name for the parent, and so it's in this case an ethyl group off of the nitrogen as well as a hydrogen that we don't name, so that's N-ethylpropanamide by IUPAC nomenclature, or N-ethyl propionamide by the common nomenclature schemes. Hopefully you're getting the hang of it. Let's pause here for a learning check just to make sure that's the case. If you would please write the IUPAC name for the following structure. So go ahead, stop the video here while you try to get that correct IUPAC name, and then start it back up when you're ready to check your work. Good luck. Okay, hopefully you did the same 2 steps that I had advocated for earlier on in the lecture. So first you find that alkane name of the long carbon chain. In this case it happens to be long, it doesn't have to be. It's just the carbon chain that includes the carbonyl. And so we see here that is a 5-carbon chain. And therefore it's a pentane that we would change to a pentanamide, or a pentanoic acid that we change to a pentanamide. And then in step 2, we look at the nitrogen. We see here we have an ethyl group and then another ethyl group. So to indicate those are on the nitrogen of the amide, we say N,N-diethyl pentanamide. Hopefully that's what you arrived at, or if you had any trouble, hopefully that's what you would be able to name it as now. If you're still struggling, please do try some other naming examples, and then certainly reach out to me for help if needed. Just like the time we took to look at aromatic amines, let's look at aromatic amides here. And so the amide of benzene is named benzamide. And there we see in this particular example, in addition to having that benzoic acid interact with an amine or an ammonia, if it was just a plain old ammonia, then we'd get benzamide. In this case, we have N-methyl benzamide because of that other methyl group there off of the nitrogen. Now let's go back and have another learning check. In this case, you're going to draw the condensed structural formulas, or better yet, the skeletal structures of the following amines. So before, amides rather, before you were taking the structure and naming, now you're taking the name and drawing the structure. So first for pentanamide, and then for N-methyl butyramide. Good luck. Okay, so we had an easy one. I hope it was an easy one. Pentanamide, so we have pentane containing that carboxylic acid that has now become an amide, or an amide rather. We have the C double bond O there, and then 4 other carbons. And then since it's just pentanamide, we have just a plain old NH2 bound to that carbonyl carbon. In the case of N-methyl butyramide, now that's a common name, right? It should be butanamide if it was the IUPAC name, but either way we associate that BUT with a 4-carbon chain, and there we have it. The carbon chain containing the carbonyls is 4 carbons long, and then we have a methyl group off of the nitrogen to give us the N-methyl butyramide. So hopefully those were both relatively simple for you. If not, if you struggled a lot with this and you're not quite sure what's going on, please do try some other ones, and then certainly reach out for help if needed. Just like we had the classification of amines, we can also classify amides in a similar fashion. So amides are classified according to the number of carbon atoms bonded to the nitrogen. Same process as the amines. In the case of a primary amide, we have the nitrogen obviously has to be bound to the carbonyl carbon, and then in a primary amide you have just 2 single bonds to hydrogen to complete the valence around the nitrogen. In the case of a secondary amide, you obviously have the nitrogen bonding to the carbonyl carbon, and then you have the another bond to a carbon from that nitrogen, and the 3rd bond from the nitrogen is to a hydrogen. In the case of a tertiary amide, then you have no hydrogens bound to the nitrogen. The nitrogen's bound first to the carbonyl that was formerly part of a carboxylic acid group, and then to 2 other carbon groups. So there we have it. Just like amines, we have primary, secondary, and tertiary amides possible. Let's follow up that discussion of primary, secondary, and tertiary amides with a learning check. Here, you're asked to give the common and IUPAC names of the following amides and also then classify them as primary, secondary, or tertiary. So this will see how comfortable you are with all these concepts that we've discussed so far with amides. Pause the video here while you complete that task and then start us back up when you're ready to check your work. Good luck. All right, so hopefully A was pretty simple. There were no real twists. It was a primary amide, which makes life easy, as you can see naming. So it's a 4-carbon chain that includes the carbonyl and then just a plain old NH2 bonded to that carbonyl. So that's by the common nomenclature scheme, that's butyramide. By IUPAC, it's butanamide. And either way you name it, it's a primary amine. We have the nitrogen bonded just to the carbonyl carbon and then to 2 hydrogens. In the case of structure B, we have the nitrogen containing an ethyl group and a methyl group, and then it's bonded to the carbonyl of what used to be acetic acid by common naming or ethanoic acid by IUPAC naming. Either way, it's an ethanamide or an acetamide because of that 2-carbon group that has the carbonyl. So if we want to name this thing correctly, it's an N-ethyl N-methyl acetamide. And again, that's just alphabetical order for those nitrogen substituents. It's a tertiary amine. All 3 bonds from that nitrogen are going to carbons. Or if we name it by the IUPAC method, it's N-ethyl N-methyl ethanamide, still a tertiary amide, and that's our solution to those 2 structures. Hopefully you were able to get the names and the primary and tertiary natures of A and B respectively. If not, please try some additional problems or certainly reach out to me for help if needed. Similarly to the amines, if we're looking at the melting points of amides, they are typically higher for the primary and secondary amides, just like the primary and secondary amines, because primary and secondary amides can also form hydrogen bonds with other molecules of that same amide, just like the amines could do, and therefore we see higher melting points. If we have tertiary amides, which means no NH bond, then it's similar to the tertiary amines, where we don't have the ability to form hydrogen bonds among molecules of that same amide in this case, or amine in the other example, and therefore we expect lower melting points. So if we look here at table 18.2, we see primary amines like methanamide and ethanamide have relatively high melting points for such small compounds, so 3 degrees Celsius and 82 degrees Celsius respectively. If we look at the secondary examples, just adding a methyl group to the nitrogen of the amide, now we see that we have lower melting points than the primary, but still higher than these tertiaries, which are well below room temperature with -61 and -20 if we add another methyl group to that nitrogen to make a tertiary amide. So primary amides are the highest melting and highest boiling, although we don't show the boiling points. Secondary are similar to the primary, although a little lower melting. And then finally tertiary are much lower melting, typically liquids at room temperature and pressure. Similarly to the amines, the solubility of amides in water tends to be decent for primary, secondary, and tertiary amides with 1 to 5 carbon atoms total, because you can form hydrogen bonds with the water, or at least be a hydrogen bond acceptor from water for the case of tertiary amides, and therefore they're soluble in water when they're small. As the carbon count increases, though, then the water solubility decreases to negligible amounts for the long carbon chains. Much like the amines we talked about earlier in this chapter, amides are useful in health and medicine as well. And so if we look at a few of the most important ones, urea itself, the end product of protein metabolism, is an amide, and it's a nice, convenient way to deal with the wastes that protein metabolism involves. Saccharin, an artificial sweetener, happens to be an amide. You wouldn't expect that really sweet behavior from an amide, but it happens to be in the case of saccharin. Just like when we talk about amino acids, aspartame is strangely a very sweet compound, although we wouldn't have expected it. So sometimes we get lucky. Saccharin was on the market, and then it was off the market, and now it's back on the market. Apparently it gave benign tumors to rats when they took extremely high dosage, but it was later allowed back on the market. Barbiturates, there's another class of unfortunately commonly abused drugs, things like phenobarbital, nembutal, and seconal. Those are some barbiturates. Phenobarbital in particular has been abused throughout the years. And then acetaminophen, which is also abused, but tends to have less severe effects, although it can do some severe damage to liver and kidney function with long-term abuse. It's more commonly just taken when it probably isn't necessary or at higher dosages than necessary, but that's used to reduce fever and pain, and it's probably the most common over-the-counter drug, I think even more so than aspirin or ibuprofen. Acetaminophen, or Tylenol as its trade name, is very, very commonly used by many people in this country. Here we see those structures of some of the things that we just mentioned. There's urea there, very simple amide, and very important protein metabolism product. Saccharin, which, as I said, we wouldn't have expected to be sweet. It looks essentially nothing like sucrose or any of the sugars, but it happens to just fit our receptors pretty well, and is actually much sweeter than sugar to humans. Then we see some other things. There's acetaminophen at the top right, and again throughout we see some other barbitals and diazepams on there. So aspartame down at the bottom is an amide because it has that carbonyl to nitrogen bond, which is the peptide bond, as you probably learned it in biology. Of course, in chemistry, it's an amide bond, and that's what we call proteins. They're not polypeptides, they're polyamides or polyamides, and the aspartic acid, phenylalanine, and a methyl ester give that aspartame a very, very sweet taste to us, but we wouldn't have predicted it from its chemical structure. So sometimes we just get lucky and we find these things that we wouldn't have been able to predict as scientists, but they work nonetheless, and that's often all we're really after. So there we have it, some amides in health and medicine, and hopefully a good introduction to amides themselves. We'll see you for the next lecture.